Yeah, so if there are any questions about the exam, just make a degree request through Grayscope. I don't think I look at that probably closer to the end of the week, but at some point this week I'll take a look at that. I should send you some more information about the final, also towards the end of the week. Today, what we're going to do is talk about symmetric matrices and the spectral theorem. This is one of the more important theorems of linear algebra. So let's talk about symmetric matrices, which we have mentioned before. Remember that the condition was for being symmetric. If the matrix equals its transpose, right? That forces the matrix to be squared. Otherwise, this equation would not even make sense because of the type. And symmetric matrices are also called self-adjoint or Hermitian in other contexts. So that's a terminology that's more common if you take a course where the matrices are allowed to have complex numbers as their entries. When the numbers are unreal, usually symmetric is relatively standard. But yeah, these two other names are more common when there are complex numbers around. Okay. But anyways, the condition for being symmetric is kind of straightforward to check because you just compare the matrix with its transpose. Now, the spectral theorem gives you like a bunch of properties of these matrices. Next time I'll tell you a little bit of why it's called spectral. I mean, why the word spectral is there. But for now, let's just look at the 2 by 2 case because it actually gives you some idea of what's going on. So let's think about 2 by 2 matrices. That's essentially how all 2 by 2 symmetric matrices look like. There are no restrictions on what the diagonals can be, but of the diagonal, the numbers must be the same. Otherwise, the matrix will not equal the transpose, right? So that's how it looks like. And that's enough to say some useful things about the eigenvalues of the matrix. So remember that for the eigenvalues, we have to look at the determinant of A minus lambda I equals 0, right? So this is the same as determinant of A minus lambda B C minus lambda equals 0, right? And this is A minus lambda times C minus lambda minus B squared equals 0. Now I'm just going to distribute that a little bit so you get AC minus A lambda minus C lambda plus lambda squared minus B squared equals 0. And now I want this as a quadratic equation in lambda. So I'll just like rearrange it so the lambda squared comes first. So lambda squared plus lambda minus A minus C plus AC minus B squared equals 0. Does that make sense? And let me know if there are any questions about the algebra so far. And then to find the solutions to this equation, you can use the quadratic formula, right? If you remember the quadratic formula, it was like in this case, like the coefficient in front of this is kind of playing the role of x squared, right? So if you remember the formula for the quadratic formula was minus b, but b is the coefficient multiplying x or lambda. So it's minus that plus or minus the square root of the discriminant, right? The discriminant was b squared. B squared in this case is minus a minus c. You get when you square that, you get something like this: minus 4a, but a is 1 in this case, times c. C represents all of that over 2a, but a is 1 again. So that's a formula for the roots that you get from the quadratic equation. Does that make sense? Any questions about this? It looks a little bit messy, but it actually will be useful in a second. It's better than, I mean, it looks more complicated than what it actually is. So let's just try to simplify this a little bit. You get lambda is a plus c plus minus a squared plus 2ac plus c squared minus 4ac plus 4b squared over 2. And this is a plus b plus minus. So if you look at these four terms, actually, it can be rewritten. The only thing that is that this 2ac after you subtract it becomes minus 2ac. So you can put this as a minus c squared plus 4b squared over 2. And now it does have a shape that you'll see it's more useful. Is that making sense? Any questions about this? So the nice thing here in this expression is that if you write it this way, you can see that the stuff inside the square root is non-negative, which is not so obvious if you write it this way, because if you write it this way, you're subtracting two things, right? So it's not so clear. But here you're just adding the square of a number plus the square of another number, right? So the discriminant is non-negative in this case. So when you have a non-negative discriminant, if you remember this thing about the quadratic formula, that means that you have two real roots. Okay, so what this is saying is that any 2x2 symmetric matrix has two real eigenvalues. So since this is non-negative, so discriminant is non-negative. So there are two roots, lambda 1 and lambda 2. So there are two real roots. Lambda 1 is the one that you get with the plus solution. And lambda 2 is the one that you get with the minus solution. So again, this is only important because if you remember the eigenvalues, I mean, a matrix may not have eigenvalues in this course because some eigenvalues would be negative, imaginary numbers or complex numbers, right? In the sense that you need the square root of -1. But this situation never happens with symmetric matrices. They will always have like real eigenvalues. Is that okay? Any questions? So the formula itself is not that useful because you can always find like the eigenvalues in practice. From once I give you like a concrete matrix, it's more to realize that you will always find eigenvalues. It's not like in certain situations where you cannot find any because the eigenvalues will be complex. This is never going to happen here. In fact, we can analyze first. So there are two real roots. That doesn't necessarily mean that they're distinct, right? So when do we get like this lambda1 equals lambda2? What needs to happen for like the roots of the quadratic equation? Yeah.
And that square root is all 0.
Right, so you need the discriminant or the stuff inside the square root to be 0. So you need a minus c squared plus 4b squared equals 0, right? But here we can say even more because again, that's the sum of two non-negative numbers. So the only way for two non-negative numbers to add to 0 is if each sum itself is 0, which is stronger than just like saying that the sum is 0. So I'm just claiming that each individual term is 0. So this has to be 0 and this has to be 0. So that like the only way for this to be 0 is for A to be C. Okay. And the only way for the second sum to be 0 is for B to be 0. So that in this case, the matrix A, the symmetric matrix, how does it look like? It looks like A, 0, 0, A. Is that making sense? In fact, so you can, if you want, write it as a multiple of the identity matrix, right? Which in particular means that it's diagonal. I mean, you can also see it from here. But the point, like what I'm trying to say is that the point in this situation where the eigenvalues agree, it's just like it's diagonal because it's like a constant multiple of the identity. So A is that making sense? So that's one case, right? Case one is where the two eigenvalues are the same. Case two would be where the eigenvalues are different. So you can call B1 and B2 their eigenvectors, right? So A B1 is lambda1 B1 and A B2 is lambda2 B2, right? So you have a 2 by 2 matrix and you have two eigenvectors, right? So what could you say about the matrix in this case?
diagonalizable.
Right, so the next best thing for us would be just to say that it's diagonalizable, and that's the case, right? So this proves that any 2x2 symmetric matrix is diagonalizable. So A is diagonalizable. So in fact, like I'll write the spectral theorem in a couple minutes, but what the spectral theorem says is that more or less this situation continues to work in the n by n case. So if you have an n by n symmetric matrix, all its eigenvalues are real, and the matrix happens to be diagonalizable. Okay, but even something more can be said. So, but I mean, it's just that in the 2x2 case we can do it because it's very concrete calculation. Like already in the 3x3 case, I think it's not so straight. I mean, I don't think there's like a proof that's which is relatively straightforward that you can just do like by so explicitly. You need something more clever. So in fact, the claim is, as I was saying, if we will be able to say a little bit more than just being diagonalizable. There's a slightly better condition. But for that, I just need another fact, which is going to happen here. In fact, so in this case, like we have these two eigenvectors, and what's going to happen is these eigenvectors are perpendicular to one another, which it doesn't happen in general if you just have like eigenvectors of like a matrix. So what's the only way we have to check whether two vectors are perpendicular or not? What do you have to compute? Yeah, the dot product should be 0. So we need to check whether the dot product of V1 with V2 is 0. Okay, so let's try to do that. So what can we say about this dot product? So the thing is, we're working in the case where the eigenvalues are different, right? So if the eigenvalues are different, at least one of these two eigenvalues has to be non-zero, right? Let's just say that this one is the one that's not 0. So you can solve, since this one is not 0, you could solve for V2. And so you could say that 1 over lambda 2, A V2 equals V2. Right. And so I can substitute that in here. Does that make sense? And I don't know if I ever said this, but like explicitly, but maybe you already kind of said that when you have like a constant, it's kind of, you can move it around anywhere you want on a dot product, so you can pull it out of the dot product. So in this case, the lambda 2 is kind of like in the denominator, so you can just put it here. Like you can do something like this. Or if you want, you can write 1 over lambda 2 times this, but kind of maybe it's easier to just look at it as a fraction. That makes sense. But then there was this formula, there was something that you could do when you have a matrix appearing in a dot product, right? I don't know if anyone remembers. There was a formula, a trick that I gave you a couple of lessons ago. What can you do when you have a matrix in a dot product?
You do the transpose.
Right, you can move it to the other, the formula is you are allowed to move it to the other factor, but the price is to move it as a transpose. So you can move this as A transpose V1 dot V2 over lambda 2. But what is the A transpose in this case? It's just A because our matrix is symmetric, right? So it just gives you A V1 dot V2 over lambda 2. Is that making sense? So here we're using the symmetry condition of the matrix. And this, what is AV1? AV1, because V1 is an eigenvector, is lambda 1 V1. Right? So what are we getting? We're getting that V1 dot V2 is lambda 1 over lambda 2 V1 dot V2. Right. And if I mean there are many ways to write this. If you move everything to one side, you can factorize V1 dot V2. And you maybe it looks better this way. And so when is a product of two numbers equals 0? One factor has to be 0. This factor cannot be 0 because we're under the hypothesis that the eigenvalues are different, right? If the eigenvalues are different, lambda 1 divided by lambda 2 is never 1. So this cannot be 0, so that forces V1 dot V2 to be 0, so that forces the eigenvectors to be perpendicular. Does that make sense? And like my point, oh, in fact, if you look at this, I mean, if you pay attention to this proof, you'll see that I never use the fact that the matrix was size 2 by 2. It's just really a bunch of properties of the dot product and the fact that it was symmetric. So in fact, like this proof works identically, and regardless of the size of the matrix, and so that will continue being true. It will be the case that for a symmetric matrix, eigenvectors that correspond of a different eigenvalues are always perpendicular. So let me write that down because that's kind of like what will allow us to improve the statement of the diagonalizability condition. So this is more or less what the spectral theorem says. Yeah, so now we're ready to write it down. So if A is going to be here a symmetric n by n matrix, not necessarily 2 by 2. So that means again that A equals A transpose. So what the spectral theorem says is that first, all the eigenvalues of A will be real. So it's kind of like a generalization of what we did here. So all the eigenvalues of A are real. B says that if you have two eigenvectors corresponding to different eigenvalues, then they are perpendicular. If B1, B2 are eigenvectors of A, so if you have two eigenvectors corresponding to two different eigenvalues, then B1 and B2 are perpendicular. Then B1 and B2 are orthogonal. And C is the most important part, which says that A is going to be diagonalizable. So A is diagonalizable. I don't know if you remember, like the condition for being diagonalizable. I mean, there were different. There were different ways to write it. This was one of like the ways you could write it. Q in this case is like the matrix of eigenvectors, right? So the idea is that you would find the eigenvectors of the matrix A and put them into a matrix whose columns are the eigenvectors. Here, B was a matrix of eigenvalues, right? So Q was a matrix of eigenvectors. And D, the matrix of eigenvalues. So that was that's in general like what I meant for the matrix to be diagonalizable. What's going to happen here, and you'll see in a moment with the example I'm about to do. But what is going to happen here is that in fact Q can be taken to be rotation matrix. Okay, so which is even better. So let me put it. So in the symmetric case, in this case, we can take Q as a rotation matrix. So now I'll explain to you how to do it in a moment. So let me call it R so that it doesn't get confused because it's a special. So it's going to be R, D, R inverse. But if you remember, a rotation matrix was orthogonal. And for orthogonal matrices, like the condition of being orthogonal is that its inverse is the transpose. So I'll put it as R transpose. So this is the equation. That's the most important equation of today. That a symmetric matrix can be written in that way, where this is a diagonal matrix, the matrix of eigenvalues, and this is a rotation matrix. So meaning, like the fact that it was a rotation matrix also meant for us that the determinant of R was one, right? So it meant like R equals R inverse equals R transpose, and determinant of R is one. That's what it meant for us to be a rotation matrix. Usually the way it's stated is that it's an orthogonal matrix, but you'll see you can always make it a rotation. You can always make a determinant one, and that's kind of convenient. So that's what we will do in the applications or problems that I'll show you later in a couple of minutes. Is that okay? Any questions about this? So essentially what, I mean, just before giving you the example, what's going to happen is that since the vectors are orthogonal to begin with, like the eigenvectors already come orthogonal, if you take these bases of eigenvectors and you apply Gram-Schmidt to them, there's almost nothing to do because these projection formulas kind of will go away. You'll see what happens. So it kind of allows you to start with a basis of eigenvectors, and after doing Gram-Schmidt, you would get like a new basis of eigenvectors. But this new basis is orthonormal, and that's the one that you take to build up the columns of this rotation matrix. So the finals, like the only difference between what you were doing before when you were diagonalizing and what we're going to do now is that now we apply Gram-Schmidt to the column, to the eigenvectors, so that it comes out orthonormal. And once it's orthonormal, you'll see that the matrix it gives you orthogonal. So I mean, these problems usually involve many steps. So that's why we'll stick to like 2x2 or 3x3 matrices so that everything is relatively manageable, because otherwise like there's too many operations involved. But like it really, once if you understand the 2x2 case well, more or less everything else is just more tedious, but like the essence of what's supposed to happen you can already see in the 2x2 situation. Okay, so let's say I give you this matrix. This is symmetric, right? Because the off-diagonal terms are the same. Okay, and then you can find that there are two eigenvalues, which are 4 and 9. So let's try to find the eigenvectors for each eigenvalue. So remember that for an eigenvalue, you have to find the eigenvectors, you do A minus lambda I. So it's A minus 4I. In this case, it gives you 1, -2, -2, 4. Right? And then you consider the null space of this matrix. Well, I mean, you do like 2 row 1 plus row 2, and you get to 1 minus 2, 0, 0, 0, 0. Okay, and this will tell you that x minus 2y equals 0. So x is 2y. So an eigenvector is x comma y, which is 2y comma y, which is y 2, 1. So the eigenvector, now for convenience, I'll write it as a column vector. So the eigenvector would just be 2, 1. Is that making sense? So that's an eigenvector that works here. So for some any question for that? So let's do second eigenvalue. So for the second eigenvalue, you do a minus under I, so a minus 9i. That gives you -4, -2, -2, -1. You do the null space of this. And I mean, again, you just reduce this. You can use the second row to kill the first one. Actually, it's more easy in this case. So you get -2x minus y equals 0. And so you get -2x equals y. So you get xy, which is x comma -2x, which is x1 -2. So the second eigenvector you can just take to be 1 -2. And no, I remember. Instead of calling them V1 and V2, I'll just call them U1 and U2, just so that I can use the same formula for branch Schmidt. I think that's up to this point. So if you look at these two eigenvectors, they are already perpendicular, right? This eigenvector is perpendicular to that eigenvector. Their dot product vanishes, which I had already said we already knew from the theory that was always going to be the case. So I mean, actually, these problems, if they don't come out perpendicular, that means that you did like a mistake somewhere in the calculations. They should always come out perpendicular. So in the past, like I'll write it and delete it quickly because that's not what we're going to do now. In the past, you would just have taken these two as the columns of the matrix, right? And you'd write 2, 1, 1, -2. And you would have said, well, this is the matrix that does the diagonalization, right? This would have been the matrix Q before. It is still a matrix that works, but it's not good enough for now for us because now we can do a little bit better. So the problem is that if you just take the matrix as it is not orthogonal. And the idea is that you can actually always make the matrix orthogonal in this situation, and making an orthogonal matrix is better because that would just be a rotation. And you'll see in the application that I'll show you in a couple minutes why that's useful. Okay. So the idea is not to take just like the first eigenvectors you find, but rather to like, modify them a little bit so that you have like a better version of that. And to get a better version of the eigenvectors, you apply Gram-Schmidt to the basis. So we're going to apply the Gram-Schmidt method to V1 and to U1 and U2 to get like an orthonormal basis. And once we have an orthonormal basis, then that's the matrix that we want. That's why I called them U1 and U2, because when I gave you the Gram-Schmidt method, that's the name I always gave to the basis without the process, and the basis after the algorithm I was calling with the letter B. So what is according to Gram-Schmidt, what's like the first the first vector? Let me put here Gram-Schmidt. So V1, if you remember the algorithm, it's just taking the first vector and divided by its length. It's kind of nothing. So U1 is like, oh, let me write it again as a row vector because otherwise it looks a little bit messy here. And the length of this vector is a Pythagoras theorem, right? The square root of 4 plus 1, so it's square root of 5. And again, now I'll put it as a column vector again to get something. Is that making sense? Questions up to this point? So that's like the first step of the Gram-Schmidt process. Now, if you remember the second step, the formula for V2 was already gets a little bit more complicated. It was this thing which involved a projection. Is that okay? So that was in general, that was the formula for the second vector in Gram-Schmidt. But these projections were like the shadows, right, that one vector makes along the other. Since the vectors are already coming perpendicular, these projections, like when they correspond to different eigenvalues, they just go away. There's no projection term here. So what that means is that this formula just simplifies a lot because you no longer have like to compute the projection. That's what I'm trying to say. So you just get this is 0. In this case of the symmetric matrices, so you just get U2 divided by its length again. Is that making sense? So that's the difference, because in the past, if you had done this when the vectors are not they're not orthogonal, then if you have like a component here coming from V1 and that scrambles everything. And so this new vector wouldn't be just like an eigenvector of lambda 2, because you're mixing like an eigenvector of lambda 2 with one of lambda 1, and then you cannot just combine eigenvectors that way. You once you add eigenvectors of different eigenvalues, you don't get like a new eigenvector. So it just gives you what? What is U2 is 1 negative 2. Is that making sense? So those are the two. Those are the new eigenvectors. So again, in this case, the fact that they were very perpendicular just meant that you just had to rescale them so that they would be on orthonormal basis. So the idea, right? Like the idea is that to use this one as a column vector, as the first column of the matrix, and this one as the second column of the matrix. So if you look at this matrix, it actually is going to be orthogonal. So, I mean, you don't have to check that as part of that. It comes for free from the fact that you're using orthonormal vectors. But this matrix was a determinant of this matrix. What do you get? -1, right? You get -1, and that's not what I want, because I want something with determinant 1, so to make it a rotation matrix, right? So we're almost there. But there was a property of determinants, right, that allows you to flip the sign of the determinant, right? So how can you flip the sign of the determinant matrix? What operation could you do? You could swap the rows, but here it's better to swap the columns. You could also do that to change the sign, because I do want to preserve, the eigenvector. So I don't want to like mess up the entries in which they appear. So what I'm trying to say is that the rotation matrix, I'll just take it to be the second eigenvector V2 followed by the eigenvector V1. So the rotation matrix is just going to be 1/√5 minus 2/√5, 2/√5, and 1/√5. So up to now, if you remember, like there was never like an obvious order in which you would like stack the eigenvectors, right? Why would you put one first rather than the other? Now there's kind of like a natural choice. You choose eigenvectors to appear in such a way that the determinant of the matrix comes out being 1. So we do like the determinant to be 1, and that kind of, in this case, will force like the eigenvectors to show in a particular form. Okay. In fact, if you if you remember, like the formula that we had from the beginning of the course, if this is really like a rotation matrix, that means that this is cosine of theta minus sine of theta, cosine of theta, right? And so that means that cosine of theta has to be 1 over root of 5, and sine of theta has to be minus 2 over root of 5, right? If you compare like the entries of the matrix, that's not like a special angle, right? So when it's a cosine positive and the sine negative, that's in the fourth quadrant, right? So this would be like an angle in the fourth quadrant. And I mean, you can check it on your calculators because it's an approximate angle. It won't be like one of the special ones. But this theta, I think, was something like 334 or whatever. Like it's just some number. It's some number in the fourth quadrant. That's what I'm trying to say. But you'll see that this is nice. This is going to be useful in a moment once I give you like an actual application about this. So what this is saying is that the matrix A, which was let me see what was that word. Five, -2, -2, 8. So according to the spectral theorem, you can diagonalize it using the matrix R. So this is going to be R, D, R transpose, where R is the matrix that we just wrote, and D is the matrix of eigenvalues. So since we use here the second eigenvector first, that you have to put in the first column the corresponding eigenvalue. So that's how we look like. Okay. And that's, yeah.
Would R be orthogonal?
It's also an orthogonal matrix. It's just a little bit better because its determinant is 1. So that's the name that I gave to rotation matrices. So rotation matrices were just orthogonal matrices with the extra condition that it had determinant 1. But yeah, if you don't care about the determinant, then you would just say it's orthogonal. But I do find it useful to just do the examples so that they always come with determinant 1, because you'll see in the application that I'll give you, that's kind of like a useful thing to have. Is that making sense? Any other questions about this? Yeah.
Okay. So if R should be orthogonal matrix, then shouldn't R inverse be R transpose?
It will be. It will. I mean, if you, yeah. No, it will be. You should find you should find the inverse of that matrix. You'll see our just do R transpose times R, and you'll get the identity if everything was done correctly. This is why, right? This is why here I'm allowed to put R transpose instead of R inverse, because if you just do like a random diagonalization, you have to put R inverse here. You cannot put R transpose. That's the important thing of putting of doing this diagonalization with an orthogonal matrix. Is that making sense? Any other questions about this? Okay, let me keep these two matrices around because I will need them later. Let's see. Okay, let me put them here. And I'll copy paste into matrix R because it will be useful in a second. Okay, yeah, so I'll keep this for what concepts. Any other questions? Okay, let me give you an application of this method to conic sections. So let's talk about conic sections. So I don't know if you remember what a conic section is. That may have been butchered from your education. I don't know. It is an ellipse, a hyperbola, or a parabola. It's one of those three. So it's like I mean, it's essentially what you get when you have a literal cone and cut it with the plane. It's just that depending on how you make the cuts of the plane, you'll get like an ellipse, hyperbola, or a parabola. So if you go to Wikipedia and just type conic sections, you can see like a nice, cute figure, picture of how you get the three different cuts or curves from doing the cuts. Okay. And they were, I mean, they have been studied since the ancient Greeks, and they are kind of useful. I mean, there are important curves, like they appear naturally in many places, so they're good to have it around. So let's let's say I have given you an equation like this, right? If I give you that equation, what does that correspond to of the three conic sections? It's just an ellipse, right? There's like a way to, I mean, this should be an ellipse. A nice way to think about it, right, is that you can make a change of variables. This prime has nothing to do with derivatives, right? It's just like new names for variables. So you could put them, capitalize them, but uppercase X and uppercase Y, but that's kind of harder to distinguish, once you start doing some writing. So it's better to, put like a prime or a tilde or something, or like some symbol to say that these are new variables. So if you just make this change of variables, it becomes like this equation is equivalent to saying x prime squared plus y prime squared equals 1, right? So now you see, oh, this is like a unit circle, right? But what's the effect of this change of variables? That just is like rescaling or stretching out stretching or like shrinking, depending on what the numbers. It will stretch or shrink the axis, right? So like the x-axis is being halved in a sense, and you're looking, and then with the y-axis you're doing something similar, but by a different amount. So essentially, if you did like if you draw this on the x prime y prime plane, you get like a literal circle. But when you try to go back to the how it actually looks like, you have to perform like a rescaling, right? And you'll get like an ellipse. I mean, you need to check which one is bigger than the other, right? Which direction is stretches more than the other. But the important thing is that kind of like after making like a simple change of variables, you can easily recognize that as a circle, right? Now, here's a little bit of an overkill, but it will be useful for what I'm about to say in a moment. So I'm claiming that there's a matrix in this picture, which is hidden from you. So I'll write this x squared over 4 plus y squared over 9 equals 1, right? I'll write this in a very odd way. So I'll write this as, well, in fact, like if you want it, that's up to you, but let's put it this way. I'm claiming that these two equations are the same thing. So let's try to understand why at least this even works just based on the size. So this is a 2 by 2 matrix, right? This is 2 by 1, right? So at least this product you can make, right? And this is 1 by 2, right? So you can also make this product. So all the products that you need to make can be done, right? And the end result should be 1 by 1, right? 1 by 1 is a number, so at least the output should be a number. So let's try to do like let's multiply this matrix times this vector. So when you do that multiplication, when you do these two first, like you get 1/4 x, 1/9 y, right? This is a simple product because they're just zeros off the diagonal. And then when you do this times this, right, you get 1/4 x squared and then 1/9 y squared. So you see, like, this is really the same as that. So I just rewrote, I just took that equation and introduced a matrix in the picture and a somewhat like artificial way, but you'll see for the next example, it will be useful to have done that. So here it kind of looks like odd that you would choose that. I mean, like, at least the eigenvalues of this matrix is diagonal, and like at least these eigenvalues are related to the numbers that you see here. But besides that, there's not too much of a reason for doing that. Does that make sense? But now let's look at a slightly more complicated equation. You'll see it's very cool what happens. So let's say I have given you that equation. Yeah. There's no point on doing that for now. The point is that it's just easier to check that this works here. But that in this case, you'll see something useful. So I was just doing it in a more simple example so that the numbers were nicer to verify. But in this example, I'm saying you can do something similar, but right, what you should put here, because now there's like a mixed term, right, like a one that involves xy, is that you should have it half it, like cut it inside by 2, so that you can minus 2. And if you do this multiplication, kind of like the same as we did there, you will get the expression above you. Okay. And now you'll see that this is doing this is useful here. It's not useful there, but it's just that here, like there, like the numbers are easier to track down. But if you compare what's happening here, it's like the x is the first entry, the y is the last entry, and then the mixed ones, right? Xy or yx is just since it appears twice, you just that's why I'm dividing it by 2. Here that you didn't see xy because it's 0xy, so that's why I put 0/2, 0/2, so it's nothing, right? But here it does make a difference. What are you going to?
Is that the same matrix?
Well, yes, it's not a coincidence, right? So, okay, first, before going there, what I was going to say is I noticed that I don't know what this is, right? I don't know if this is an ellipse or a parabola or a hyperbola, because I have this thing in the middle that's, confusing me, right? Like, I don't know what to do with this thing. Like, it's not so clear, like, how this should look like, right? In this case, it was easy because there was no combined term. So what's about to happen is now I have a symmetric matrix, and I'll take advantage of the diagonalization procedure. So if you remember, this is exactly the matrix A. Oh my God. So like this is the matrix A, but A is R transpose, right? So you can rewrite this as R transpose right? But like let's plug in everything. That's why I didn't want to erase nothing on this side. So I don't need this matrix anymore. And I won't need this after I replace that everything there. So I'll put like let me put it here. X, Y. R is this one, 1/5, minus 2/5, 2/5, 1/5. That's R, right? D is 9004. And R transpose is the last term, right? But I just transpose, I'm just going to transpose this one. So I just replace A with R, D, R transpose, right? So this is R, D, R transpose. That makes sense? And now I'm going to do the product. I mean, there are like 5 things I can need to, like, 1, 2, 3, 4, 5. I'm going to do the multiplication kind of in a useful way. I'll multiply this with this and this with this. Kind of, I'll leave the diagonal matrix alone for a while. So when you do this multiplication, you get, okay, so again, this is 2 by 1 and this is 2 by 2, right? So you'll get like another 2 by 1. So you get x over root of 5, x over root of 5 minus 2 over root of 5, comma, 2x over root of 5 plus y over root of 5. Okay, so when you do this product, you get this. And when you do this product, you get what? You get x over root of 5 minus 2 over root of 5 y. And then 2x over root of 5 plus y over root of 5. Does that make sense? Here, y. Yeah, thanks. Thank you. Anything else? No, I think that the rest is fine, right? So, anyone see how are these two vectors related to one another? Is there any clear relationship between them? Right, like there's like the answers are the same, or one is the transpose of the other, right? Like, so the cool thing is that if you were to call this x prime, right, and this one y prime, right, then this is what? X prime, y prime, right, times 9004 x prime y prime, right? And now, I mean, this more or less kind of looks essentially identical to this, right? You got rid of the diagonal terms in a way. And so this equation, like remember, all this was being set equal to 36, sorry. So if you look, this should correspond to 9x prime squared plus 4 y prime squared equals 36, right? And if you divide it by 36 on both sides, you kind of end up with more or less the same equation as before. So now it's clear that this should be an ellipse, right? Which is one was not obvious before, right? So doing the diagonalization, like, and also like, that's also why it was useful to have like an example first, where there were zeros on the diagonal, so that you would recognize that it's just, you get something without mixed terms. So what this is saying, remember that we are accomplishing this with a rotation matrix, right? I think the angle was like 336 or something like 334 or something like that. I told you. So what that means is that if you x prime, if you look at what x prime is going to be, if you rotate this by 336 degrees, see if I let me put it this way. And then, I mean, I want to say that this is kind of 324 degrees or something like that. Or 334, I don't remember the angle that I gave you last before, but it's the angle of rotation that we have found in this matrix. So if you do that, yeah. Oh, right. So going back to myself. So if you rotate the x-axis by that amount and the y-axis by that same amount, which is the same as kind of rotating clockwise by 26 degrees or the complement, then it is on this, with respect to this rotated axis, that this looks like the equation of a regular ellipse. So you get like an ellipse that looks somewhere like here. So otherwise, there's no good way to know that this was going to be an ellipse if you don't perform the rotation. So it is like literally how you draw like an ellipse, like in general, but you just have to draw it with respect to the new axis. Does that make sense? So next time, what I'll do is I kind of give you like the method, write it out explicitly of how you can take a conic section and apply this theory and get like a new get an equation you can recognize easily as an ellipse, a hyperbola, or a parabola. This is actually the way you can also prove the second derivative test in multivariable calculus, because essentially you can do like a Taylor expansion for a function. And when you do like a Taylor expansion for a function, you get like the second derivative with respect to x times x squared plus the mixed derivative xy with respect to xy plus the second derivative with respect to y twice times y squared. When you do like the Taylor expansion, and then you get like a symmetric matrix, which is called a Hessian, and then you would diagonalize it. And once you diagonalize it, then you can find what you're supposed to, whether you get like a max or a mean or a saddle point based on the eigenvalues of the matrix. It's just that that's not typically how it's, given in multivariables, because not everyone has seen like eigenvalues by that point. But really, the second derivative test is just if you wanted to write it more nicely geometric, you would say you find like a 2x2 symmetric matrix called the Hessian, and the eigenvalues of that matrix tells you whether you get like a parabola, a max, a mean, or a saddle point. Okay, so but yeah, so next time I'll just write this down more precisely, the method, so that you know what you're supposed to do. But this is kind of like one nice application of symmetric matrices, which is kind of unexpected, because like up to this point, you have never seen like x squared or y squared in this course, right? Like all the x has always been raised to the power 1. And now all of a sudden you see like you can also use linear algebra, even when like there are more variables involved. You just have to be clever on how you introduce the matrix. Okay, but yeah, I think this is a good point to end because we only have 10 more minutes. So on Wednesday, I'll write this stuff down, and then I'll tell you other applications of symmetric matrices before we talk about projection matrices, which is another important topic.